Calculus BC, Lesson 1.5, Functions and Logarithms. Review for most of you. If not, you've got a lot to do. What's a function? It's a relation with unique outputs for every input. I just made that up off the top of my head. I sure hope that's accurate, but it doesn't matter because I always graph it. And it means let's do a little better than that. Passes the vertical line test. So no matter what kind of vertical lines I put in there, it only hits once. So it's a one-to-one function. It's a function with unique inputs for every output. Passes the horizontal line test. For example, this diagram that I've made above, not one-to-one. So definition and functions one-to-one on the domain, blah, blah, blah. Just showed you what it means. By the way, you can make something a function by limiting the domain. For instance, an absolute value is not one-to-one unless you say, well, I just want the negative side, or no, I just want the positive side. So the domain will go from 0 to infinity, or from negative infinity to 0. So leads to a question, which is, who cares? Well, this is kind of important. If I can set up a good model, which is what a function is, and define something going forward, it means that one-to-one will define it going backwards. By the way, those means define a good model. I'm shocked that how many people don't know that. Backwards. So it works both ways, forwards and backwards. That's kind of important. I mean, I come up with a good model for predicting what the temperature will be on any given day of the year, and it works. You have to think, does it work going backwards? Well, the temperature outside is 60 degrees. Well, that could be March 18th, or it could be October 15th, or something like that. So that would not be a one-to-one function. It's not a really good model going forwards and backwards. So this gets us into inverses because we're talking about forwards and backwards. So an inverse means just flip it. So I'm going to use y equals. And before I flip it, I'm going to solve it. So otherwise, I just find it gets a little confusing. So get x alone. And I may have screwed this up, as I am wont to do. But then to write the inverse, you would say the inverse is negative x over 2 plus 2. And the good thing is, if I did screw this up, I'm about to find out. Because when we do a composite function, we take f of x, which is negative 2 times x plus 4, and we plug in the blue thing here. we do the mathy thing. X minus 4 plus 4 equals X. That means we did it right. This ties nicely together in that y equals x reflects these two functions. So here's y equals x. Actually, I'll give that a different color. Let's go with the inverse function in blue. Negative x over 2 plus 2, so it starts out up here, goes down 1 over 2, down 1 over 2. So here's your inverse function. Here's your original function, negative 2x plus 4, 1, 2, 3, 4, down 2 over 1, down 2 over 1. And it's not a perfect drawing. It's pretty good. It's not perfect because right here is the y equals x line, and they reflect through that. Hard to see with that, but if you do it with other functions, it's a bit easier. However, in the interest of time, we've kept it fairly simple, the function and the inverse. So use the composite to say, okay, it's an inverse, composition to say it's an inverse, and then we graph it to make sure it graphs properly. And it looks like it did. So let's do it parametrically, which everybody groans, and you better get used to parametrics. They're not going anywhere. So we will set, we can do a lot of things. Let's do x equals t and y equals t squared. See if that makes sense. Y equals x squared. Yeah, that works. And since we have defined that there, we're going to have to define it here. T has to be greater than or equal to 0. Excuse me. And how do we find the inverse? That's the function. Now we find the inverse function. Real complicated. Flip them. I think t still has to be greater than or equal to 0, but I might be wrong. I'll have to graph it and check. So I could easily do this on a calculator and actually recommend it, but let's just do these in colors real quick. When t is 0, we're at 0. When t is 1, x is 1. 1, 2, 3, 4. 1, 2, 3, 4. It's up here at, once 1 is at 1. No, it's not. When t is 2, we get 4. When it's 1, we do get 1, but I'm going to leave that off. We get 4. Yep, that's right. Just had to make sure. So it actually does it here. There's my function. Here's my inverse function. Hits at 0 and 1. And then at 2, it hits out here at 4. And here's my y equals x line. Let's just do it parametrically. Really not that complicated. The other way to do it is to say that, like we said before, y equals x squared, get x alone, x equals square root of y. Since we're only dealing with the positive stuff, I don't need to put a plus minus in there. My pen's taking a holiday. That should do it. Oh, it doesn't want to work. Of course not. I'll just go on with crossouts. So sorry about that. Just had some pen problems. See if it works. So we go here and say f of -1 equals, pardon me, the inverse of f of x equals square root of x. And again, where x is greater than or equal to 0. So, what's the inverse of y equals a to the x, blah, 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 blah. All that. And why the limitations? Well, if a is 1, this is kind of pointless. It's 1 to any power. And if a is not greater than 0, then things get very strange. So we just make sure it's a positive number. So the inverse, well, we have to do the logarithm thing. So we say log base a of y equals log base a of a to the x. And we get, these two cancel out, of course. X equals log base a of y. And flip the x and the y. Y equals, might as well be consistent. Y equals log base a of x. So they're inverses. What's the domain and range of a logarithm? I don't think there's an I in there. Yeah, there might be. Well, let's look at the other one. Exponential function does this, at least before it gets shifted and all that, and it hits here at 0, 1. Well, if they're inverses, then we should get that flip across the y equals x line, something like this. And it hits here at 1, 0. So the domain is not including 0 to infinity, and the range is all reals, which we write as -infinity to infinity. So quick refresher to see if you remember how to do that. I just showed you, but I'll do it again. Rewrite this. You can write as 2 to the y equals x and flip it. So that's y equals 2 to the x. That's the inverse of this. And over here, you can write log base 3 of y equals log base 3 of 3 to the x. You get x equals log base 3 of y. Flip them, and that's the inverse. Y equals log base 3 of x. And you know this because when you graph them, that's what you see. So if you haven't been told that, one of the big reasons for logarithms is that you get an inverse function. So what's ln of x? Well, that's natural log. It's French. Although, again, I've looked it up, and it's extremely argued over. Nobody's sure. So the base is base e, exponential. Base for log with nothing there is base 10. And these are the two you'll find on your calculator, and nobody ever writes it that way. So it's just going to be y equals natural log of x. In case you forgot your log properties, solve for x. Well, we'll take e to the power there and e to the power there. So get x equals e to the 3t plus 5. And there's nothing else to solve. We don't know what t is. Over here we say, okay, let's take natural log of both sides. Cancels out, get 2x equals natural log of 10. X equals natural log of 10 all over 2. A lot of people blast it out in the calculator, and you're more than welcome to, but you do not have to. And some log properties, similar to exponent properties. If we're multiplying, we can break it apart and add. If we're dividing, break it apart and subtract. If we're taking to a power, we can throw it out front and multiply, so on and so on. So a lot of people say, well, how am I going to handle a log base 2? And I just say, when in doubt, do that BOI thing and see what happens. So BOI is base to the outside equals the inside, BOI. Had a student teach me that. So we go 2 to the y equals x. Now take, let's say, natural log, which is a nice one to use. of both sides. You can throw the y out front. Not equals, my bad. Divide natural log of 2 both sides. We get y equals natural log of x over natural log of 2. So you can use this to graph, where you do log of x over log of 2. Actually, I'd prefer to put that in natural log, so I'm going to clear that and do it again. Natural log of x divided by natural log of 2. And to prove that's the case, we actually have a change of base formula on this calculator. Not all of them have it. So just graph base 2 of x. And graph them both. It takes its own sweet time. That's the first one with the change of base formula. This is the one based on what the calculator says it should be. You can see they match up right on top of each other. So then we get lots and lots of applications. Sarah invests $1,000 in an account, earns blah, blah, blah. So write it out. How long it take to get 2,500? 2,500, what she gets. 1,000, what she starts with. Simple interest, 1.0525 to the t. Divide by 1,000. 2.5 equals 1.05. 1.0525 t. Could use any log. Again, we're going to get used to using natural log. Throw the t out front. T equals natural log of 2.5 over natural log of 1.0525, which equals, I'm using my own calculator just because it's a little bit faster. 17.9 years. Long time. That's about it. Happy mathing.